Выход.
No, nie.
No. Okay. Okay, so let me start. I guess more people will come or something. So last time I defined this category. Wait, maybe how do I pick different color? Yeah, thanks. Okay, so last time I defined it's black, I see. Okay, let's try again fourth time. Last time I defined this category, DM effective of geometric motifs in this, right? And so roughly speaking, this is kind of a down-to-earth definition, I guess, would be chain complexes in your of finite correspondences of this category. So that means that chain complexes of schemes, but with morphisms coming from here. And modulo somehow, you want to make somehow one, like you want to make the affine line contractible. So trying to mimic homology or homotopy theory. And two, you want to kind of deal with kind of sheaves in some sense. And the correct way to say that in this setup is to say you have some Merviatores. Sequence. Okay, and like, because the idea is we want to compare this category to later, maybe, to the classical category or of pure motifs. So maybe say up to numerical equivalence. So this is like pure motifs coming from smooth projectives. Because we want to compare later on, we also like do some pseudo-abelian completion of this. Because this category was built by completing, by adding kernels and co-kernels of projectors. And again, we do that because we want to split the diagonal divisor and to get some maybe Kunet thing. So there is a reason why we do pseudo-abelian completion, or maybe in the literature also it's called Karubian completion. And as I mentioned, like this setup, it's not quite powerful enough to, and somehow like a better framework is to work with sheaves. So you can apply like sheaf cohomology, machinery from sheaf homology, sheaf cohomology. So today, like, we define the sheaf theoretic version of this category of geometric motifs. Yeah, I mean, the effective here is not really so important. It's the fact that we're working with geometric things. I mean, really like algebraic cycles, which are difficult to deal with. I mean, if you just look at Fulton's book, it's very hard to prove basic things. And just sheaf theory, when you have a sheaf and have like local information, you can just get things, you can get more done. Okay, so in this way, like what would be the right notion of a pre-sheaf here? So you might want to be tempted to write just, I guess, a pre-sheaf to be something from the category of smooth separated schemes to a billion groups, let's say. So AB, a billion groups. So, but we want to encode correspondences, right? So this is not good enough, and we work rather with our finite correspondences. Okay. So this is kind of seems to be a good definition of what a pre-sheaf is. So something like a functor from this category to a billion groups. And we also want to encode somehow like this localization information, right? Because we're going to build our sheaf theoretic version of this guy, and then we're going to, of course, compare it to the geometric guy. So we want to mimic this process.
Should this functor be additive or not?
Yeah, I mean, like, it depends what you mean by like functor, like as pre-sheaf, I guess, but like later I will just talk about sheaves mainly, and sheaf by definition is kind of additive. So yeah, it's true that like in Vygotsky's definition of like pre-sheaf, he defines, he says like, let's just consider additive guys, but for our purposes, it's not necessary to do this, like, especially since we just go to sheaves fairly quickly. So like like we want to see what the analogs of these guys are in this framework. Like Meyer-Viatori sequence, like that's not really, I mean, that will just be the sheaf property, whatever that means in a moment. I mean, to consider sheaves here, we need to consider a certain topology and things like this, so we'll get there. But A1 contractibility may be something like this. So we call a pre-sheaf, so such a pre-sheaf, so in Vygotsky's terminology, is homotopy invariant. Again, like thinking of A1 being like the interval 0, 1, hence the choice of language. If the natural map from f of x to f of x affine line is an isomorphism. Where this map here, where coming from some projection, the projection map. Okay? I think that's like a natural definition of what A1 contractibility means here. And somehow pseudo-abelian completion, okay, we're going to talk about like what it means for it to be a sheaf here, just now. But like for later on, like we're going to end up with a category, a Grothendieck category. When you define a category of sheaves on coming from like a Grothendieck topology, you end up with a Grothendieck category. So our category will be a billion. So there will be no need to talk about pseudo-abelian completions in this framework. It'll be better. Yeah? So, but we do need to talk about what a sheaf means here. I guess the above is right. So, like, we have like smooth category of smooth schemes separated, coming in fully faithful, I guess, living in core finite correspondences. So, like, I don't know how people are familiar with like Grothendieck topologies, but it's certainly much more natural to put some kind of topology definition on here, like what covering means here, right? Not on this guy. So this is like, there's some choices here, like what topology do we put on here? Do we put on the Zariski topology? Do we put on the Étale topology? Do we put on something else? In reality, you can put on any topology. So for the Zariski topology, some things don't work. And for the Étale topology, also some things don't work. And as a result, like, there is a topology in between, which is not really used outside of like this world of motifs, at least. Well, it is used in K-theory quite a bit, but the right notion is like the Nisnevich topology. So just in case, I mean, I recall the definition. So Nisnevich covering. Okay, so basically, so our family, this is something in between a Zariski topology and an Étale topology. So like for K-theory, for example, K-theory doesn't satisfy descent for the Étale topology, but it does for the Nisnevich. So this is one reason why it's natural to set up a framework with the Nisnevich topology, because later on we want to compare motifs with K-theory. I mean, that's like one of the motivations from building motifs. So a family of Étale morphisms, I don't know, does everyone like, has everyone seen like what a Grothendieck topology is? Like in, yeah, okay. A family of Étale morphisms like UI to X is a Nisnevich covering. So the Nisnevich topology was introduced by Nisnevich, I think he's a Russian mathematician, like in 1989, I think. So if like, so for all points x in X, there exists some point ui in some ui. So we pick out like this pi ui to x, mapping ui to little x, such that, so at this point it's just an Étale covering. Like we just cover all points in X, such that the induced map on residue, on residue fields, k of x to k of ui is an isomorphism. So again, like up to here, like this part here is just definition of Étale covering. But I'm also, in the Étale situation, like you may have a finite separable extension here of separable of the residue fields, but here we're saying that they're isomorphism, and somehow like this works very well for K theory. But I give an example for a difference right now. So for example, so if I have like such a covering, like let's say A1 minus some point A1, and where A does not equal 0, and then A1 minus 0 to A1. So this is like as a risky I, and I consider the map Z gets mapped to Z squared here, and this is just say, yeah, inclusion. So this is an étale covering. Alright, maybe assume also, like just in case, characteristic of K is equal to 0. But it is a Nisnevich covering, like if and only if this point A is actually a square. So there is some kind of like the Nisnevich site or covering or whatever is picking out like some kind of arithmetic information, like a little bit more finer arithmetic information than the étale situation. And as a result, for example, so more generally, local rings in the étale topology are strictly Henselian. So just in case, like, you have the structure sheaf for every scheme here.
Maybe the bottom row should be square, top row should be inclusion.
What's that, sorry?
Maybe bottom row should be Z maps to Z squared, and top should be inclusion. Because Z maps to Z squared is not étale in 0, I guess.
No, is it? Because no, I think this is fine. Like, you think this is not étale?
But at 0 you have unification. No?
I mean,
No.
yeah, but so you think this should be inclusion here, and this should be Z goes to Z squared.
I think yes.
But how am I going to get this condition here at the end?
And you need to have some pre-image of A, which comes from K. And if A is not a square, then the pre-image on the square is not rational. It will be not. It will be not rational point of A1. So yeah.
Yeah, maybe you're right.
I think it's just a T.
Yeah. Yeah, I think that's better. Thank you. Yeah. Otherwise, like away from this thing, you just get something strange. Yeah. Thank you. Yeah. Okay. So yeah, like if I have like my scheme XOX here with the structure sheaf, then in the étale topology, like if I localize this to look at the stalks, then I get like strictly Henselian local rings here, which means that, like, you know, the local ring satisfies Hensel's lemma, and the stalks are, well, and also the residue fields are separately closed, And in the Nisnevich topology, so like you just get Henselian because somehow this condition of like isomorphism in residue fields, you can't like keep extending all the way up to the separable closure as you can for the Ital topology. So yeah, you just get Henselian. Okay, so let's state one fact and try and prove it. So, proposition, sorry, I forgot to, before this, I forgot to define one more important sheaf. So, so by the way, like such sheaves, like, sorry, I forgot to define like what a sheaf is. Okay, so definition. So a free sheaf F from finite correspondences to abelian groups is sheaf if like F restricted to the smooth guy is a sheaf for the Nisnevich topology. So such a thing is called like a sheaf with transfer, I guess. So you have an honest sheaf like on the smooth for the underlying schemes. But you also have like this module structure coming from correspondences, so you get a sheaf with transfers. Okay. And I guess like whenever you start talking about sheaves, like you want to look at the free sheaf. So let me do that here. So definition of the free sheaf. So for X, a smooth separated scheme, then we have this, a priori we have this free sheaf defined by just your homomorphism set, right? Group. Okay, so like whenever you start defining like the sheaf associated to your underlying geometrical objects, or sorry, the pre-sheaf object, you want to check whether it's a sheaf or not. Like this such a notion is called like subcanonical site. It's not necessary for this guy to be a sheaf because we may be able to sheafify it, although it's not at all clear like what sheafification means in this setting, because like we're defining like sheaf on like a not even a full subcategory, but like a subcategory. So what does sheafification mean? It turns out like you can make sense of it. So assuming there is such a notion of sheafification, then like you want to, if this is not a sheaf, then you can certainly sheafify it and things like this, but it's the theory, it's much easier when you have a subcanonical site, so when this is a sheaf. So let's check it. So, proposition. This free sheaf. I say free. I mean, in the sense, I guess, in algebraic topology, when you just have the sheaf generated by X, but the ZTRX is a sheaf. Okay, so let's try to show that. So we need to check two conditions here. So we want to check that, like, for P U to X, a Nisnevich color surjection. I mean, we can always group many coverings into one map. Everything is like finite type here. We have the following sequence. Maybe I should put Y here, sorry. So ZTRX of Y to ZTRX of U. By the way, like this pre-sheaf structure, like the maps are given by composition of correspondences, finite correspondences, which I didn't like explicitly like verify that it works out, but it does, because the correspondences are finite. So this map here, for example, is given by composition of correspondences. I mean, like here you have like a correspondence from X to Y, some correspondence. And here you have just a map, from Y to X, the other way around. From Y to X, yeah. And you just compose with the map P to get a correspondence here. So this is just P composed with, say, correspondence, which is another correspondence. Finite, well, it's finite as well. Okay, and you have, so you have you want to check that the sheaf condition is satisfied, basically. So we want to check that for a Nisnevich surjection. We have that this sequence, this sequence is exact. And like, yeah, okay, because I didn't define like pre-sheaf to be like an additive functor or anything like that, then I also should check that like you have some additivity property so that I can group or covering into one guy. So you want to check that Z, this transfer sheaf X of some disjoint copy of U to V is indeed like just the sum. But I think like this is like pretty straightforward from the definitions. So I think one will be, let's focus on one. Okay, so Yeah.
Basically because the correspondences is extra categories.
Yeah, exactly. Yeah. This follows automatically. I agree. Yeah, one goes like this. Yeah, this requires a little bit of thought. So, proof of one.
Also, one minor thing, we consider only finite as named couplings, so in order to group things together.
We consider only what? Finite.
Only finite couplings. So I mean with finite amount of.
Yeah, exactly. Well, I mean, here I only consider a single one, actually. Is that what you mean?
Group all of it together.
Yeah. When we're allowed to group all of them together officially because of this. So proof of one. So like here, we have like, let's show exactness. So let's show exactness at, let's say the middle term first, at z tr x of u. So the middle guy. Okay, so we have some like correspondence here, z, and we suppose that like it gets mapped to 0 via the diagonal map. So this is the map going from ztrx of u to ztrx of u cross product. So this basically gives us some descent datum. So like the fact that like your section or your course, well, in this setup, your algebraic cycle or whatever gets mapped to 0, this is equivalent to giving some descent datum. For z along, let's say, u, along our surjection or covering u to y. Okay, so we need to produce from like this information. So we need to produce a cycle on y times x, basically. So, i.e., an element of ztr xy. Okay, so one natural candidate is the following. We have our cycle on u times x, and we have a map induced via our covering to y times x, and we have, so z here, right? So we can make a definition. So z candidate to be just the closure of z along this map, along p times id(x). And this will give you like some kind of, this gives like let's say just an algebraic cycle on y times x, but like a priori we don't know whether it's a finite correspondence. So the surjection to y is finite. And here we use faithfully flat descent. So like, because z was finite over the u part, I guess. Let me check. Yeah, the u part. Then like you get finiteness over the y part. So basically what I'm trying to say is like z being finite over u plus descent datum star, which is this part here, gives you that this z candidate is finite over y by faithfully flat descent. Again, there's some like unraveling of definitions here, but the point is that like what is really going on is that like if I have a faithfully flat map here, so like a Nisnevich covering is in a tau cover by definition, so it's smooth, so it's flat, so like all the tau morphisms are flat. If I have a flat surjection here, and I have like something finite over the source, then together with descent datum, I can descend that down to something finite over the target. In other words, finite maps satisfy descent for faithfully flat maps. Faithful just means surjection here. I mean, this is really important. There are other sorts of properties which satisfy faithfully flat descent. I mean, I'm just using finite here because that's all I want. Like I'm trying to get back a finite correspondence. Is that kind of clear or yeah? Okay, great. And like, okay, so there is like exactness at so the left part. So like, I'm sorry I rubbed it out, but I hope something's visible. Yeah. If you haven't written it down, then I can give you my thing if you need it. Okay, so here, so we have like you want to kind of somehow show injectivity here. So we can assume basically. So this is like using the technical thing that I didn't write down last time, but like the fact that like our finite correspondences are surjective over some irreducible component. So we can assume y is irreducible because our finite correspondences by definition, the technical part that I didn't write down, is like, yeah, they're surjective over, they lie completely over some generic point, let's say. So, i.e. y has a single generic point. So in this situation, like z, which is our element in ZTRXY, is finite over y. Such a finite dominant map is completely determined fiber of y at the generic point. And I can convince you y of y. So basically, like, the situation is like you have a finite map. So the base has a single generic point, and you have a finite map. So you just forget everything and just like, let's just focus on this situation where you have y, a irreducible guy with a single irreducible with a single generic point, and you have a finite map which surjects onto it. So whatever the fiber is at the generic point, that determines the structure basically, because a finite map is basically, you can cover y with, say, affine schemes, and because this is finite, somehow the projection of it will also, the starting point will also be affine by definition. So you have like spec A to like spec of B, and this determines what B, the structure of B should be. And because, of course, like all of these spec of A's, they're covering the generic point. So it's enough to be, yeah, I mean, the official proof, I guess, is in Stack's project, but like the saying is that like a finite dominant map is determined by what happens at the fiber at the generic point. So in short, we can basically kind of assume y as a point here, and then like this map here is no longer like some complicated composition, but just pullback of algebraic cycles, because you just have like an algebraic cycle on X, and you want to produce an algebraic cycle on U.
The cycle on X, which is finite on points, so it's just a bunch of points, right?
Well, yeah, that's true. Yeah, maybe this whole thing is just like a trivial structure. Yeah. But yeah, you can do it that way, I guess, as well. But the way I was thinking anyway was like, essentially, this is like a composition, but the official definition, and it's difficult to verify the injectivity. However, like when y is a point, this just reduces down to like pullback of cycles, or as you said, like you just have a point here essentially, and this easily to check. I mean, you're just checking whether some inverse image of a point is again like non-trivial, like non-empty. So you get injectivity here, and I mean that's like the easy. I would say that's the easy part of the argument. In the middle is the difficult one. At least like, yeah, you need some faithfully flat descent, which is I would say non-trivial. Okay. Okay, great. So we know ZTR is a sheaf. And finally, like we want to sheafify things. So we want to sheafify things just like because sheafification is like the basic thing you can ask for when you're dealing with sheaf cohomology, right? And also because we want our category that we construct to be like sufficiently nice to construct injective resolution. So like such a thing is like a Grothendieck category, and the minimal amount it asks for is like there is a sheafification functor. So the right way to say it is as follows. So let maybe I didn't introduce some notation, so but let nis trk be the category of Nisnevich sheaves with transfer. Yes? Okay. So that just means like it's a sheaf on the correspondences, but like restricted to smooth, you have satisfying some sheaf property with respect to the Nisnevich topology. Then the functor, the inclusion Oh, sorry. So of Nisnevich sheaves to say pre-sheaves. Sheaves with transfer. So has a left adjoint which is exact. So this is just a fancy way of saying like there is a sheafification. Sheafification is always like usually a joint with like the inclusion functor from sheaves to pre-sheaves. We can try to prove some parts of it, I guess. Let me try. Okay, so we need like some tool first of all. So we need this lemma. Maybe I won't prove all of it because otherwise we just may run out of time for other things. So suppose like suppose I have this situation. So yeah, suppose I have like a Nisnevich cover. And I have a finite correspondence. Then in a lot of the arguments, it helps to you often have like something like a finite correspondence composed with like a Nisnevich cover, but it's helpful to kind of swap them around in the following sense. So the statement is that there exists some V here, such that this map here, so this is the, let's say, the starting datum. Let me make that clear, otherwise I'm gonna get confused. So this here is the starting datum of what's given. So the statement is that there exists some V. Yeah. There exists some V smooth scheme such that n maps like this, such that this is also a Nisnevich cover. And this is a finite correspondence. Which makes the diagram commutative. So, like, the way we'll apply this is like it'll, as I briefly mentioned, in some situations we'll have like some finite correspondence followed by some Nisnevich cover or something, and we can, by this lemma, we can swap them around and then like, yeah, make things easier again on using this side. And I mean, the point is that Nisnevich cover is like an honest map, and these are like not honest maps, so they're a bit more difficult to deal with. But by flipping things around, like, you can kind of kill off things one by one. At least, that's like the very loose idea. Okay, so let's try to prove this lemma. So like we have like a proof, yeah, there's proof here. So we have this finite correspondence x to y. Let me make it a bit bigger. So we have like this finite correspondence. So this is basically saying that like we have some z inside x times y, and it's finite over x. So there's like a very useful fact, like when you have a finite map over a Henselian ring, then the source is just a disjoint copies of Henselian rings. I mean, it's a very nice property of Henselian rings, which is often used in étale topology, which allows you to make local arguments very nicely, which you can't do in the Zariski setup. And here we can do the same thing because we have Henselian rings. We don't need strictly Henselian. So the point is that like we have this like let me write Z here again, and we have it living over U, or am I mistaken? Yeah, X is here. Yeah, so Z lives over Y, and we have some Nisnevich covering here, U, in part of our datum, and I let ZU be the fiber product. And at the same time, I have here X, which is finite. So this means that like locally for the Nisnevich topology, so there exists some Nisnevich cover, say V here, such that if I pull back along here, let's call this, yeah, just without introducing too much more notation, just the actual fiber product, and here something. So I think here, like, you're inside x times y, and I think if you work it out, then this fiber product here, whatever it is, it will be inside v times u. So that's just by unraveling like all the fiber products. But the point is that, like, what I'm saying is that there exists a Nisnevich covering such that this map here splits. So there exists a splitting. So what's going on here is the following. If I reduce all the way down to a point, I get a Henselian ring here. And because this is finite, this means that this becomes a disjoint copy, a finite disjoint copy of Henselian rings. And because this is a Nisnevich covering, or an étale cover, then an étale covering of over a Henselian ring splits. And now, like that's happening at the co-limit, and by taking a small neighborhood of that point, I can just move up to my Nisnevich cover and get the splitting around a small neighborhood. Like generally what happens usually at the stalk, you can extend to a small neighborhood of that point. So you get some splitting here, and the claim, I hope that's not confusing. So you get a map S from Z times X to V inside V times U, and like this section like gives a correspondence from V to U, and because Z was finite over Y, by following the diagram, this correspondence will be finite over V. And I mean, in short, this finite correspondence becomes this map here. And by kind of the way we constructed it, you get a commutative diagram as a result. Okay, let's try to apply the lemma. Are there any questions on that? Like, I think the takeaway, at least, would be that, like, you know, when you have a Henselian ring as the target and you have something finite over it, then the top is just a finite copy of Henselian rings. And when you have an étale cover over a Henselian ring, then it emits a section. So basically, in short, like Henselian rings in the case of finite maps or étale coverings are like incredibly nice. And this is actually, I mean, that's what makes a lot of arguments in étale topology work, and also in this setting here, because, well, in étale topology you have just the strict, like you just have a strictly Henselian ring. Here you just have Henselian, but that's enough. So it also is what makes the things here work for the Nisnevich site. And see that, like, if we started working with the Zariski site, we would be in trouble here. I mean, at least like the current argument doesn't work. And so, yeah, you can still make the theory work. I'm not really aware of, like, I'm not really familiar with how to do it, but clearly it's going to be much harder, because in the Zariski topology you just have local rings, and none of what I said, like for finite maps over a local ring or a Zariski covering of a local ring, like that, you get nothing for free. Okay, so let's try to use this lemma to prove at least one thing. So I'm trying to prove sheafification. Can I get rid of this board? So I want to show the following. So, like, let F be a pre-sheaf. Wait.
Go back.
Go back? Назад?
No, yeah.
Here. Means. Okay, thanks. Let F be a pre-sheaf with transfers so let F Nice be the sheafification of F restricted to the category, the honest category of geometric objects, smooth separated schemes, for the Nisnevich. Topology, so that's like a completely okay operation. Then there exists a unique Nisnevich sheaf G with transfers, so extending F Nis to the whole category of finite correspondences, so such that G restricted to the geometric objects is equal to F Nis and there exists and equipped, equipped with a morphism of pre-sheaves. F Nis. Sorry, F to G. Okay, this is just like a long way of saying that we can do sheafification in the correct way. Let me just prove, yeah.
I have one question.
Sure.
So, does this lemma work for étale topology, for example?
Absolutely. Yeah, I mean.
And for FPPF?
But like for the FPPF, what are the local rings? Like not Henselian, right?
Like this.
So I think so I don't know. I mean, but maybe because like the FPPF has enough descent to like do something maybe, and especially like you have finite maps here, so it's possible.
So in principle, we can build theory for any nice topology.
Yeah, I think so. Like, I mean, and in the literature, like he does, Vygotsky, that is, when he did this work, he did like he did consider like the étale setup, and he like what we're trying to do now is like we're building a category of motives in the sheaf sense right now, but for the Nisnevich topology. But he did it for the étale topology. He calls them like étale motivic sheaves or étale motivic complexes.
So because he needed somehow to compare with étale homology.
I think the natural topology actually is étale topology, but one of the main motivations for setting up motivic things like this is due to Belinsson, I guess, and his idea was to compare, like, interpolate K-theory somehow. K-theory lives by itself, but like using geometric objects, like schemes, you want to connect them together somehow. And using, in the end, the right result is like motivic cohomology is precisely K-theory in some sense. And there, once that result holds for étale motivic sheaves and Nisnevich sheaves, but once you start like wanting to do arguments for the K-theory side, like K-theory satisfies descent only for the Nisnevich topology, and that's the reason why Nisnevich created his topology in his paper, 1989 paper. So I think like if you want to work with like, so motivic cohomology is the same as K-theory. However, if you want to get results on the K-theory side, then you're forced to work with Nisnevich topology, basically. And there is such a thing called Zariski motivic sheaves. And in this setup, like it's more to do like using Vygotsky's language. This is like related to something called pre-theories, which is like, I mean, his notation, his language for it. And I'm not sure how he goes about it. I didn't like read properly, but clearly like I don't know what he does to make things work, but clearly something works. But that's a good point though. Like what does FPPF here do? I haven't seen that in the literature even considered. But like, if it does work, then that's something that could be considered, that could be interesting to consider, and to, maybe is there such a notion of like FPPF motivic complexes? I don't think that exists in literature, but maybe if such a result like could be improved for FPPF, maybe you can do something, and that could be interesting for like a paper. I don't know. It's a good question. Okay, so I'm going to try and leave this. Yeah, okay, let me get rid of. So I'm just going to try and prove uniqueness for G here using this lemma. Otherwise, like it all seems a bit disjoint. I think I can remove this because like this is not much. There's not much going on here. So, to prove, like, show uniqueness of G, let's say. So what we want to do, like, clearly it's unique on the smooth thing because like by definition, G restricted to smooth was equal to F-nis. So you don't have much choice there. So what you really want to do is like, given a morphism, F x to y, so a finite correspondence, we need to check that suppose there are two such guys. G1 and G2. We need to check that G1 of F is equal to G2 of F, basically. So as morphisms, basically, right? Morphisms from G1 of Y to G1 of X. I mean, on objects, they're the same thing. G1 and G2 are the same. We just need to check it's on morphisms. I mean, on objects, you're fixed. So basically, we're going to use this lemma. So let Y be in, say, G1 of Y, which is equal to G2 of Y. Then, using this lemma, we choose a Nisnevich covering U to Y, such that, so choose U to Y, a Nisnevich cover, such that Y actually comes from our original sheaf. So such that Y restricted to U is the image of some U So remember, like G1 and G2 were sheafifications on the geometric objects of F. So locally, that means each section comes from some honest section coming from F. Okay. And then basically we can, by this lemma, we can construct a V such that this holds. And then we make the computation. So let's call this map, I think here, I called it F. So this will be F. I think let's call this P. Let's call this F prime and P prime. Then we can make the following computation. So G1 of P prime of G1 of F. So that's going along here of Y is equal to G1 of F prime, G1 of P of Y. That's just by commutativity, which is equal to G1 of F prime of Y restricted to U. And because Y restricted to U is coming from an honest section of F, and G1 and G2 are the sheafifications of F, that must be the same as G2 of F prime of Y to U. And just expanding everything out again, this gives us G2 of P prime, G2 of F of Y. So basically what we've shown is that up to some cover, namely P prime, that G2 of F and G1 of F are the same. But because G1 and G2 are sheaves, then they must be the same. Okay. So I won't prove like the construction of how to actually sheafify it at this point, at the moment. But so in any case, like we can make a good definition now of let's say the sheaf theoretic version of DM of geometric sheaves, motives. So we have our category of Nisnevich sheaves with transfers. This is now a Grothendieck category. Dick category because there is a sheafification functor. There is a sheafification functor. So because of this, like we can consider the derived category of Nisnevich of such sheaves, right? I mean, you can take the derived category of any abelian category, but like if you want to do computations, you need injective resolutions. And injective resolutions are only guaranteed usually when one has a Grothendieck category. So that's why it's good to have sheafification. So, and because like we're trying to imitate homology theory, and we don't want to work with unbounded complexes for now, And because we're trying to work with homology theory, it's better to put bounded on the right. So complexes go, like, there's a lot of terms a priori in the left direction. I mean, this is normal for homology theory. And then we just localize at homotopy invariant sheaves. To get this category D, so the quotient category, sheaves such that f of x, so f of x times a1 is an isomorphism, and this by definition will be our candidate of motivic complexes, or at least effective motivic complexes. So are the steps kind of natural? I mean, we're trying to consider correspondences as morphism sets. So this gives rise to sheaves with transfer. Then we want to do homology theory. So we take the derived category. And then we want to imitate the construction of geometric motives. So there we localized, or we made A1 contractible. So in this case, we quotient out by homotopy invariant sheaves like this, to in the hope of comparing later. We don't need to, localize by any kind of mere Vietoris things. It's already done here because we're considering sheaves, right? Mere Vietoris is just giving sheaf structure. And we also don't care about pseudo-abelian completion because we get a Grothendieck category. It's abelian, so it's much nicer. Okay, of course, like the derived category is not an abelian category. Like it's going to be a triangulated category, but it turns out that actually it will be pseudo-abelian. That's in this case. I mean, our triangulated category will be Cherubian. Such a notion makes sense. So this is like our category of motivic complexes, and for the next few lectures, we'll start to compare this motivic complex category to our geometric category, and what will happen is that this will live inside this motivic complexes, and everything that we'll only be able to prove non-trivial statements essentially only here, because we have access to sheaf cohomology theory. And then by fully faithfulness, we'll be able to transport results back to our intended category of geometric motives. So it's a powerful, I think, yoga, where, I mean, often you start with a category that you want to study, in this case, geometric motives. It happens to not have enough structure. So you put it inside something bigger, and where you have more objects, but there's more structure as a result, and you prove things in this bigger category, and this gives you results back in your original category that you wanted. So that's the point. I think we can stop there for now. Do you know how I stopped this chipping?
Change to computer, right?